Brian, why is the cosmic microwave background so significant to our cosmological models, and in particular to the standard model, which is inflation theory? And what are the kinds of research that you're doing, particularly with the Simons Observatory, to address that question?
So the cosmic microwave background marks the kind of maturation of our field from an art to a science. Its discovery in 1965 provided the first physical evidence in terms of standard measurable quantities of watts of energy, of watts of power, of microwave energy, of spectrum, of black body radiation that was basically an open and shut case, that the universe was once in a much, much hotter, much, much denser state. It didn't prove the Big Bang happened, but it proved the conditions of the universe at a time a few minutes after something happened, whether that was the collapse of a pre-existing universe as the initial interpretations led to first projected it to be, or whether it was a Big Bang singularity. We still don't know the answer to that. However, we know very accurately and precisely what's occurred since the formation of the elements, the evolution of those elements, of hydrogen, etc. And the formation of hydrogen allowed this heat trapped from the initial hot, dense phase of the universe to cool off. Once neutral atoms form, then microwaves or light waves can propagate through an expanding universe. They expand, cool, their redshift increases. That means their wavelength increases, their number density decreases. The combination results in a much more diffuse, much lower energy collection of photons that we nowadays observe as microwaves. The famous 2.7 Kelvin microwave background discovered in Holmdel, New Jersey in 1964 and 65. That ushered in a quest. Again, the progression of science, at least in cosmology, is a new observation, sometimes serendipitous, in this case it was, leads us to poke holes at the pre-existing observations and knowledge of a pre-existing model, refining it, making it better. Soon, though, the kind of flaws in the Big Bang model started to emerge. Why did the universe have these peculiar properties? Why was it so flat, so homogeneous, so free of magnetic monopoles? That cried out, demanding an explanation that didn't exist until Alan Guth proposed the inflationary universe. And that too has its lacunae and its gaps and its flaws that we attempt to plug holes in or to bolster and to maybe come up with alternatives. The most conclusive smoking gun, if you think of inflation as the spark, as I call it, that ignited the Big Bang. If you think about the Big Bang as an explosion, which isn't really correct, but it's a useful kind of analog. If you think about who pulled the trigger, you know, the implications of what we do are so astounding. It's not only scientific, it's not only to do with microwaves and resistors and telescopes. It has to do with philosophy, with theology perhaps, and metaphysics. So the stakes could not be higher, and it all started from this cosmic microwave background. What caused the cosmic microwave background? What caused the elements to form? What caused the bang to be in the Big Bang? That's inflation. So it cried out for an explanation on its own. The smoking gun, the smoke from the gun, if you like, of inflation are called primordial gravitational waves. This is sought to be perhaps an even bigger discovery than the Big Bang itself, because it's really instantiating how did the Big Bang come about. So we set out on a quest in the early part of this millennium to measure the gravitational wave background using a small telescope located at the South Pole called Bicep. It's a refracting telescope of a Galilean design, which I think is quite tickles me. And this telescope did discover the gravitational wave background, this primordial background of B-mode polarization. It was astounding. And as predicted, the world erupted in celebration, front page of every newspaper. And that showed you, and it was a shoo-in. Everyone's going to win Nobel Prizes for Alan Guth, maybe for team members on the Bicep experiment. Maybe even for me, I don't know. But it was not to be. So the signal that we detected was not a blunder. It was not, you know, we didn't leave the lens cap on the telescope. We didn't have our thumb in the frame. Instead, we measured not the B-mode imprint of gravitational waves, themselves sparked by inflation. Inflation, perhaps the consequence of a multiverse or a god. But instead, we measured the imprimatur of cosmic schmutz, of space schmutz, of dust, of micrometeorites, if you like, permeating and suffusing our galaxy, but not our cosmos. So that was the kind of letdown. But the reaction to it around the world did bespeak of the fact that humanity is intensely interested in understanding our cosmic origins, including the origin of inflation, because that would be potentially the origin of the Big Bang. The moment that was happening, the press conference that was at Harvard Center for Astrophysics up in Cambridge, that press conference, I got a phone call in my office. Very strange. I recognized the voice immediately. It was Jim Simons, one of the richest human beings on earth, called the world's smartest billionaire, mathematician, code breaker, philanthropist. And he asked me, he said, Brian, what's going on? What's going on? Indeed, I couldn't really speak to the fact of how I felt at that moment, having come up with the original Bicep 1 idea and wanting to be a part of this huge discovery, but not knowing if it was really right. Of course, it was found to be not a blunder, not, as I said, not a mistake, but we retracted the interpretation that it came from inflation. So that left a door open that we could do an improved version of this Bicep experiment. Not sensitive to a single electromagnetic wave frequency, as we were with Bicep 2, but we could measure a whole broad spectrum that could include the effect of the inflationary waves of gravity that we're interested in seeing, but also of the cosmic space schmutz that we want to get rid of. So that's a systematic error. Those systematic errors can only be removed by application of another experiment. In this case, we build an experiment with lower frequencies and higher frequencies than the CMB.
You can average them out.
And then we average them out. We subtract it out. And that became the Simons Observatory. With my colleagues, Mark Devlin, Suzanne Staggs, Adrian Lee, and Jeff McMahon, we have built a team of 300 people and brought them to the world's highest construction site in the Atacama Desert of northern Chile. We're building 4 telescopes, which will eventually become 7 telescopes, joined by European and Japanese collaborators. And this will make the deepest search ever for these cosmic microwave background, B-mode polarization, gravitational wave, harbingers of the imprimatur of inflation.
Okay, just quickly describe why that's the case, why the B-mode polarization are a direct consequence of inflation. Why does inflation lead to those primordial gravitational waves, and how sure are you of that? We know what the inflation theory says. We know potentially what you could measure with the B-mode polarization, but what is that theoretical linkage that makes you so confident?
Right. So inflation is predicated on the existence of a quantum field, a scalar field, like the Higgs, may be the Higgs, we don't know, but this quantum field, like all quantum fields, has what are called fluctuations, uncertainties, ripples, or perturbations. Those perturbations have different types of characteristics. Some are called scalar perturbations and some are called tensor perturbations. The scalar perturbations provided the seed for structures of dark matter and ordinary matter to agglomerate in specific areas in the early universe, as we have observed with temperature measurements from Planck, South Pole Telescope, the
1 in 100,000.
These, Kobe experiment, exactly. These are large-scale fluctuations that are incredibly, incredibly small. If you think about the average fluctuation, as you said, 1 part in 100,000. That's smoother than the surface of a bowling ball. That's smoother than the surface of the Earth.
But it's all you need.
That's all you need. And my colleagues are so impeccably excellent at building sensitive technology that our detector quality made by my colleagues, they are able to make detectors that are improving faster than Moore's law in terms of sensitivity increase with time. It's doubling on a faster time scale. And we're making more and more of them. And of course, these aren't just, put them in your iPhone. We can't make them exactly like that, but we're making them to operate at almost zero pressure and almost absolute zero temperature to make these detections. So what are they looking for? They're polarizers. So they're looking for an imprint of polarization. That polarization, the type of polarization that has a twisting, curling pattern, is called B-mode polarization. That can only be produced by waves of gravity. And those waves of gravity can only be observed to make a cosmological imprint if they occur on regions larger than the horizon size, at which time the CMB formed. So they have to appear at regions that are so widely separated, just like the horizon problem of inflation.
So that they couldn't, there's not enough time for them to have communicated together. So if they are the same, it bespeaks of their mutual origin as opposed to a
Randomly,
community
right.
randomly, or some sort of a homogenation that they occurred together.
Right, late time evolution,
Yeah.
which would be the case if the alternatives were true. So they would have much, much lower levels of gravitational wave background.
What's the time frame?
So we're getting first light, the very first photons, or first microwave as we call it, in 2023, and then the full observatory begins operation on Jim Simons' birthday in April of 2024. He'll be 86 years old. He'll come back down. He broke ground with me and my colleagues back in 2019. He's promised to come back down and see this just incredible. It's the largest, most ambitious experiment of its kind ever performed.